Okay, this is example 3.9, and here we're going to look at the principle of conservation of linear momentum. Okay, so just like energy is conserved, momentum, linear momentum, angular momentum, these are conserved as well. Okay, let's see what happens when an object breaks into two parts. Suppose an astronaut floating in space throws a 0.5 kilogram away. The mass of the astronaut is 100 kilograms, and the camera moves off at 6 meters per second relative to the astronaut. What happens to the astronaut? So the idea here is we have this thing called linear momentum. It's a type of motion. It's the mass of the object times its speed, its velocity, right? mv, mass times speed. What we would say is that the principle of conservation of linear momentum would state that whatever the momentum is for these two objects together at the beginning, before the astronaut throws the camera, should be equal to the linear momentum after the astronaut throws the camera. Okay, so the system is the astronaut and the camera. There's an event occurring where he's throwing it. The total momentum should be conserved, should be the same throughout the whole process. So let's start off at the beginning. So this is before throwing the camera. The total mass would be 100.5 kilograms. And the velocity, the speed, is 0 meters per second. It doesn't state that there. The idea is that we're just assuming that from the reference frame of the astronaut holding the camera, right? Holding the camera. Assume you're not moving, you're just floating. Then you throw the camera. Well, normally on the Earth, that's not an issue, but it turns out throwing a camera in space presents an issue that has to be resolved somehow. And that is because of momentum. The momentum at the beginning, before you throw the camera, is 0, right? Why is it 0? Well, there's a mass, 100.5 kilograms, but the velocity of the astronaut and the camera is 0. There's no speed. Therefore, because the speed is 0, the momentum is going to be 0 as well. So we would say the momentum is 100.5 kilograms times 0 meters per second. Well, that's going to be 0. Now, after you throw the camera, we have to have the same amount of momentum that we began with. So if we began with 0, we have to have 0 here. There can't be any overall momentum. But we've got two objects now. We've got the astronaut and we've got the camera. Those two together have to equal 0. We're not going to claim that every particle is not moving. We know that something is moving. The camera is moving away from the astronaut. That means that the two momenta added together, that's the plural of momentum is momenta, these two momenta will add up to be 0, right? That's the conservation law. So what do we know? We know the camera has a mass of 0.5 kilograms and has a velocity of 6 meters per second. But we don't know much about the astronaut in terms of the velocity. The velocity is unknown, but we do know the mass of the astronaut. And we do know that when we add that to the camera's momentum, mass of the camera times speed of the camera, those two together are going to be added up and they're going to be 0. Okay, so let's go ahead and write that out. We have 100 kilograms, that's the astronaut's mass, times the velocity of the astronaut, plus 0.5 kilograms, that's the mass of the camera, times 6 meters per second. And that's got to add up to 0, right? See how that is? Because this right here is the momentum of the astronaut, This right here is the momentum of the camera. We already know that those two added up together have to be 0. Mass times velocity, mass times velocity. Now here's what happens. There's going to be some value of the speed of the astronaut because those two numbers, if they add up to 0, you can't have either one of them be 0, right? This number right here, 0.5 times 6, this is 3 kilogram meters per second, right? I just did the arithmetic in my head. 0.5 times 6 is the same as a half times 6, which is the same as 6 divided by 2, which is the same as 3. But we have this other term here for the astronaut, 100 kilograms times the speed of the astronaut. So now we have to do a little bit of algebra. We have to figure out the speed. So what I'm going to do is I'm going to first subtract 3 from both sides. Remember, whatever you do to one side, you got to do to the other side, right? So plus 3 minus 3 is 0. 0 plus -3 is just -3. Don't worry about that's negative. It turns out we need that to be a negative. 100 kilograms times the speed of the astronaut. I'll put it all in parentheses there. Okay, so all I did was I subtracted 3 from both sides so that you have 100 times the speed of the astronaut all by itself. Second step, I'm going to divide both sides by 100 kilograms. Now look what happens on the left side. 100 kilograms cancels and you've got the speed of the astronaut. On the right side, -3 divided by 100 is -0.03. The kilograms cancel and you've got meters per second. Those are the units we would expect for speed, meters per second. So that's just the algebra part, right? Not really physics there, it's just the algebra. Here's what turns out being the case. The camera, after the astronaut is disgusted because it doesn't work, is moving off at 6 meters per second. The astronaut is now in a bind. He didn't think about this. He didn't think about physics. He's now drifting off this way at -0.03 meters per second. Now that's about 3 centimeters per second, which isn't that much, but you know, if you multiply that by 3,600 or even 60, if you multiply that by 60, you get 180 centimeters per minute. Okay, well, that's about 1.8 meters per minute. So every minute he's going to float off about 1.8 meters, which is about 6 feet or so. Okay, so he's going to be every minute 6 feet away from his space station, because he got angry, threw the camera away, and then floated off in the opposite direction.